Alrighty, here is a second idea for the Le Chatelier's principle. Heat, whether or not something is an endothermic or an exothermic situation, where heat is at. So either heat is going to be on the left-hand side of the equation over here, right? And if it is, then we consider that to be an endothermic situation, where delta H is greater than 0, positive, or heat is going to be a product of this reaction, in which case it is an exothermic situation where delta H is less than 0 and heat is given off. So how are we going to tell? Well, what we're going to do is we are going to take some solid ammonium chloride. You see that it's solid here. And I'm going to put it into some water, and we're going to see if this water gets hot or whether it gets cold. So first of all, I'm going to go ahead and take and put a thermometer in here so that it can acclimate, because if this is an exothermic situation and I put sodium or ammonium chloride and put it in water to make it aqueous here, if it is an exothermic situation, then it is going to give off heat, and this guy here will get hot, and we'll notice that the temperature goes up. So again, that is if it is an exothermic situation. If it is exothermic, then heat is going to be a product over here. It's going to give off heat, and it will therefore get warm as the water absorbs it. So it'll be delta H less than 0. Heat will be given off exo, and it'll get warm. Heat's a product over here. Or it's going to get cold, which means that it needs heat to do this. So heat is going to be over here on the left-hand side. And if heat is over here on the left-hand side, then it's not going to be an exothermic situation. It's going to be an endothermic situation, and it's going to get cold. So it's going to take heat and the solid to go with the water in order to create these aqueous compounds over here, these aqueous ions over here, and so therefore it should get cold. So here we are. I've got it right now. It is currently at room temperature, which is about 21 degrees Celsius. So right now I am sitting pretty, I don't know if you can tell this or not on the camera, but I'm right at about 21 degrees Celsius there. There I am. Yep, you can see that pretty well. Okay, so now what I'm going to do, set that off to the side, is I'm going to take some of my solid here, some of my solid ammonium chloride, and I'm going to put it into my container of water here and let that guy dissolve. So put that in and stir, stir, stir. And you will notice right off the bat, boom, look at what's happening to the temperature. The temperature is now down to well below 20 in the 15 zone. So this is definitely getting colder. And again, I can feel it here. We don't have feel-o-vision yet, so you can't see it, but that's what the thermometer is for. The thermometer definitely went from about 21 to way less than that. Now it's already down to about 12 or so. So this guy is definitely getting colder for this. So what does that mean? That means that we have an endothermic situation. So what's happening is that the heat is going here, and the heat is a reactant. So it's requiring heat to go with the solid to turn it into the ions here. It is an endothermic situation. So what do you think is going to happen to all of this solid material that's down here if I were to take this and I were to put it into a hot water bath? So I've got a hot water bath across the room. I'm going to take this test tube here that's still got solid in it, and I'm going to raise the temperature, and I'm going to make the heat go up. So what's going to happen if I make the heat go up? Which side will it shift to, and what visual representation will we see because of it? Well, if the heat goes up, it'll send it to the opposite side, which is away from the solid, and it's towards the dissolved side. So by raising the heat, it'll send it over to the right, which means I'm going to have less solid and more ions. So I should see, when I do this, I should see this solid material that I have here dissolve when I put it into a hot water bath. So here's a hot water bath. like so. You can see I've got some boiling water here. If I put that in and give it a little shake, 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 Sonora, and give that a minute or so, and get that good and stirred, I should see that that solid dissolves here. All right, I'm going to go get my thermometer in order to stir it. Although that's probably bad practice and I shouldn't be stirring with the thermometer. But if I stir this guy with a thermometer, boom, we can see that the solid is now all dissolved and there is now less solid in there than there was before. And so consequently, we have used Le Chatelier's principle to shift the equilibrium. Now, if I take this and I let it cool over time, what's going to happen is all of that is going to come back and it's going to recrystallize out, because if I cool it, what's going to be happening is the following. If I cool it, then that means that instead of adding heat, I'm going to be removing heat. And because heat is on the left-hand side of the equation, if I remove something, then that's like trying to take something from a 2-year-old, it's going to want it back. And so by cooling it down, I will send it back over to the left-hand side, and eventually as this cools, I will recrystallize out all of that solid that was down there, and it will eventually end up down there at the bottom once it gets cool. So Le Chatelier's principle, once again, if you add something, it'll go to the opposite side. If you remove something that affects the equilibrium, it'll go to the same side.